Hi, I'm Ben-Yaakov. This presentation is entitled Back to Capacitors Basics, and this is part 1, Decoupling. There seems to be some confusion concerning terminology, functionality, and the use of capacitors. For example, there is some confusion as what is a decoupling capacitor, what is a bypass capacitor, how do they function, and how to specify them. Now this is the part 1 of hopefully a sequence of videos that will cover the various uses of capacitors in electronic systems. So let me start with the issue of decoupling. Now if we have a system like a power supply, a DC source, a battery or power supply, and then say a converter, a switcher, then there is a problem here in that this switcher is generating pulses which are injected into this high voltage, while the source may also have noise, and there is a need to sort of separate the two, not to allow the noise from the source to penetrate into the inverter or our system in general, or for this ripple to actually go back to the source. This will be like an EMI issue here. So there is a need to separate the two, so decouple them such that the noise or spikes or ripple generated by this switcher will not penetrate into the source, and then that the noise from the source will not go into the system. Now in many publication posts and videos, you'll see that the explanation of the decoupling capacitor is that we need to put a capacitor here such that the ripple or the injection of current into this high voltage line will sort of be captured by this capacitor. Okay, so this is the idea of the decoupling, supposedly. This is wrong. The reason is that in this presentation, when you have a DC source, a capacitor will not help anything, because the internal resistance of a source, a DC source, a battery for that matter, or even a power supply with a large capacitor at the output, the impedance here is very low. So consequently, the injection here, the current, the spikes, the ripple, will still go over here, because this is sort of shunting the capacitor. And you may need an infinitely large capacitor to capture all this current. It's just impossible. Now the real situation and the real remedy to the problem is to have an impedance here. In a physical system, you always have some impedance, the line impedance. Usually, however, it will be small, because you like to reduce the stray inductance, you like to reduce the resistance, you're going to use a ground plane so that the inductance will be small. So in a real system, without doing anything, this impedance is really small. So in order to really decouple the two systems, you really have to introduce an impedance here, such that the impedance of this capacitor will be much lower than this impedance, and then most of the current of this injection, of this noise, will be captured by this capacitor. Actually, the same thing goes here. If you have a noise here, and if you just put a capacitor here with no impedance, then still you'll have this noise coming in into here. Part of it will go into the capacitor, but still you'll get some of it across the line here. So in order to improve the attenuation, you do need an impedance. So an impedance is really a key in actually the decoupling concept. Now, this impedance could be a ferrite bead, we'll talk about it a little bit later, or could be just a resistance if the DC drop is acceptable. That is, you like to put here a resistor, but obviously if there is a DC current here, then there is a voltage drop, and sometimes it's not acceptable, sometimes you can actually tolerate it. So these are the possibilities. Obviously, in a large system, if this is like a line or an input or a battery to a system, you may need here actually a full-fledged filter, both for common mode and differential mode. I'm not going to talk about this. I'm just talking about a sort of local circuit in which you have a local power supply, you have a local system you have to feed, and the interconnection between these two. So let's go back to the basics of capacitor. What is a capacitor? A practical capacitor can be modeled by this simple circuit in which we have the capacitance, which is the energy storage capability of the device. This is the capacitance that stores energy, and this is responsible for lowering the impedance, 1 over omega c. And then we have a stray inductance. This has to do with the structure and depending on the way the capacitor is built. And then we have the ESR, which represent the dielectric losses. Now the ESR is causing losses because the current that is passing here, the AC current, the spikes, the ripple, is generating heat, I square ESR, and this of course will limit the amount of current or the magnitude of the current that is allowed in this device. Also, it is causing some attenuation. We'll talk about it a little bit later. So let's see how a capacitor is behaving when you expose it to pulses. I have here a case in which I'm injecting a pulse of 1 amp with a rise and fall times of 1 microsecond. Duration is 1 microsecond and the period is 10 microseconds. Here the red are the pulses, and as a result we see now the ripple that will be generated on here on this capacitor. This is the ripple, and in this case we see that the ripple, the amplitude is about 1.5 volt. Okay, so this capacitor may be just not good enough or not large enough. But if I change some of the parameters, and in particular if I change the inductance, and also I'm changing here the rise time, okay, the faster rise time and a larger inductance, see what happens. Aside from the triangular ripple, we see here these spikes, which are very large. This is very typical of a fast switching system in which you have fast pulses, high rise time, and you'll see also these very nasty spikes. So what is determining the waveform? On the one hand, we have the operation of the capacitor as a charge storage, so that when we have the pulse coming in, this is the pulse and it's zoomed in, the area here is a charge, and this charge is increasing the voltage, and then delta V, the increase in the voltage, this is the ripple, will be the charge minus the current that goes to the load at this particular period, divided by the capacitor. So the larger the capacitor, the smaller will be this amplitude of this triangular waveform. On the other hand, the spike is due to the IDT and the inductance. So the larger the inductance, the faster the IDT, the larger will be the spike. This is now the spike. You see that it is like a constant voltage as long as you have the IDT here. And for our case, 100 nanohenry and 10 nanosecond of a rise time, here it is, we get 10 volt, and this is just about what we are getting here. Okay, so these spikes are due to large inductance and fast the IDT. So we can already understand that these two are really very harmful, and one should avoid them as much as possible. You need small inductances, and then you need low the IDT if you can. Now if it's a fast system, there is a problem. So what can be done? Well, one way, which is very, very popular, is to put another capacitor in parallel, which has a much lower inductance. Now notice that this spike is really not dependent on the capacitance. The capacitor is a short during this transition here, because this is a very high frequency, and therefore this capacitor doesn't play any role in this spike. So if you put a capacitor which has a lower stray inductance, it could be of a lower value, and indeed the inductance is a function of the structure. The smaller the capacitor, supposedly, the inductance will be smaller. So this is from where this idea of putting a 0.1 microfarad capacitor is coming. The capacitance doesn't matter that much. During this transition, you have very high frequencies, so 0.1 microfarad is okay, but a smaller capacitance capacitor will hopefully have a lower inductance because it is smaller. So let's have a look what is the reality. I'm showing here the impedance of two capacitors. This is from KSIM of Kemet. This is the impedance of two capacitors. This is the blue one and this is the orange one. The blue one is 0.1 microfarad, here it is, and the sort of yellow or orange one is 1 microfarad. Both are X7R and both have the same package. This is the same package, okay? So I'm putting these two together. So I'm putting these in parallel, and hopefully, so as the common wisdom says, put 0.1 microfarad. So I'm putting 0.1 microfarad, and what I'm saying is the following. This is the impedance of the 0.1. It's higher because it's a smaller capacitance. This is the 1 microfarad. It's lower. So here, no wonder. And then we have a resonance between the capacitance and the inductance in the two cases. The resonance of the larger capacitor is at a lower frequency. The resonance of the 0.1 is at a higher frequency. Now, the idea was that I want the capacitance of 0.1 to have a impedance which is lower than the impedance of the 1 microfarad at high frequency. Well, this doesn't happen here because you see that the impedances are just about the same. So as far as this circuit goes, if I take out the 0.1 microfarad, the system will behave the same. So you see, it's not a matter of just the capacitance of this capacitor. It has to have a inductance which is lower than this inductance, otherwise it doesn't help. So here I'm showing another case, and in this case I have two sizes. One is the 1210 and 10603, the 0.1 microfarad. This one is smaller, this one is larger. Still, even for this difference, we see here the impedance of the 0.1, we see the impedance of the 1 microfarad, and then there is a region here, this region here, that the impedance of the 0.1 microfarad is indeed lower than the impedance of 1 microfarad. Well, you see that that's really not that significant. I'm showing here an AC analysis of these two capacitors. I have extracted the inductance from these resonant frequencies. So here is this inductance, and here is this inductance. Well, you see the inductances are not that much different, okay? Really not that much different. In fact, the 0.1 is a little bit higher. I don't know if it's correct, but it's very close. Now, obviously, the resonant frequency will be at a higher frequency because the capacitance is lower. So this explains this shift here between these two. But the inductance is just about the same. So if we look at the total impedance now combined, we see the 1 microfarad, and then the resonance of 1 microfarad, and then it becomes inductive. This region above resonance, the capacitor is shorted, we are left with the inductor, and therefore this portion is inductive, and now the 0.1 microfarad kicks in. It's lowering the impedance, well, but not that much. Okay, it's lowering, no question about that here, as compared to this. This would have continue like this, so here we have an improvement, okay, but that's not a very big improvement. It is an improvement, especially around this frequency, but it's not what we sort of expected. Now, if I take the case of a electrolytic capacitor, which has a fairly large inductance, then obviously I would like to have a 0.1 microfarad. That's okay. And this is like a real capacitor, 150 microfarad. It's a 100-volt capacitor with a 50 milliohm ESR. And this is the 0.1 microfarad capacitor we saw earlier with 22 milliohm. We see the impedance of the electrolytic capacitor is just about constant here, and then it goes up, and this is sort of the resonant point. As far as the 0.1 microfarad go, you see here nicely the impedance going down. We see the resonance, and then it goes up. This is everything is fine. Now, when we look at the combined parallel assembly, lo and behold, we have here a peak here, a very high impedance, very high resonance. Why is that? Well, it is because we have here, in this region here, an inductive behavior of the electrolytic capacitor. We have here still the capacitive behavior of this ceramic capacitor. So L and C here, with a low resistance here, high Q, total resistance, is actually creating a resonant network, parallel resonant network. It's parallel because we have this capacitor. It's parallel because we have here the inductor, the larger one, and it is in parallel with this 0.1 microfarad. This contributes a little bit, but practically it's these two together. And this is very nasty. This is very, very nasty. Now in the time domain, when you look at it, what we see, I'm injecting again the fast pulses here to the combination of the electrolytic and the 0.1 microfarad capacitor. What I'm showing here is each one operating by itself. That is, this is just injecting to the electrolytic capacitor. So we see little low frequency component here because it's a large capacitor. But we have very large spikes because of this inductance. And here I'm showing the ripple that you'll get if there be no electrolytic capacitor, just a 0.1. Well, you don't see the spikes, but the ripple is very, very high. Okay, well, it's 15 volts peak. So this is why you need a capacitor for the storage of the low frequency ripple. Now, when you combine the two, well, we see here the low frequency scale doesn't show us exactly this difference here. We show it also here, but we see now the oscillation due to the interaction between the inductance of the electrolytic capacitor and this low capacitance of the ceramic capacitor. So this is not so good. So on one hand, we eliminated these spikes here of this electrolytic capacitor, but we generated quite a bit of noise here, high frequency. So things are complex. On the one hand, it sort of helped. On the other hand, it generated its own problem. So I'm going back to what I've said before. Whatever you do, you are going to have some noise here, some ripple, some spikes. And to be on the safe side, if you would like to eliminate the injection or reduce or attenuate the injection into the source, you do need a impedance here. Now, if the injection is very high, that is very high currents, then we need capacitors which are capable of capturing and handling these high currents. And this is a case in which you would need a snubber capacitor, which is designed specifically for this application, in which you have very high dIdt and very high current, so they can tolerate it. I'm not going to talk about it in this presentation because I'm limiting myself to the lower power, but this is another subject that hopefully I'll discuss in a forthcoming video. Now, what about a ferrite bead? A ferrite bead is supposed to introduce a impedance here. Now, ferrite beads are not inductors. Well, they are combined inductors and resistor. And the idea is that you actually need a resistance, but you cannot just put a resistor because of the large DC voltage drop. So you have a resistance which is a frequency dependent, and this is due to the actual losses of the ferrite material. So it's a combined inductance and resistive behavior. And here I'm using a very simple model of a ferrite. This is from TDK. This is actually operation of the ferrite, you might say. You see that it has an inductance, but then it has a resistance, and then there is actually a capacitance, because at very high frequency the impedance actually goes down. And I'm just picking this for a demo. I have not selected it in a proper design procedure, just picked this particular one. It has a 0.29, 290 milliohm DC resistance, and here's the capacitance, inductance, and resistor. So I'm now showing the effect of this ferrite on the circuit, of the decoupling circuit. When I have now a source, I have now a switcher. It's a 1 amp with a 100 milliamp pulse riding on it. I have here a electrolytic capacitor. I have here a ceramic capacitor, 0.1, according to the, well, let's call it the book. Everybody knows, well, you have to put a 0.1 microfarad. And then the same thing here, except that here we have a ferrite. Now, to be fair, I've put here a resistor of 290 milliohm, because it will be unfair if this will be just a straight line. As I've said, if this is DC, then the situation is really different, okay? Because then obviously this is sort of shorting the bus here, this voltage source. So this sort of resembles the same situation. But before that, let's have a look at the impedance of the bead. And this I'm doing in an AC analysis. This is now the bead, and I'm running here an AC analysis. And here it is. We see the impedance of this bead, ferrite bead, and then this is the phase. Now, as you can see, the phase here is toward 90 degrees, so it is inductive. So in this region, the bead is inductive, and this region is 1 megahertz to 10 megahertz. Only after fairly high frequencies, like 100 megahertz, this particular bead, sort of the impedance goes high and the phase goes down toward zero, meaning that here actually it is a resistor. That's very nice, because the DC is very low, while the resistance is 42 dB, which would be like 100 ohm. So this is excellent, but it's really not relevant to the circuit we are talking about, okay? It's too far away. This is the region we are interested in, so rather than putting in a resistor, we have put in an inductor. And this is what happened, because now, if I compare these two, this is without the bead, just the DC resistance of the bead, and this is with the bead. Looking here and here, this is comb is without, and comb ferrite bead is with. You see, you got now oscillation. While without the bead, you don't have the oscillation, you have a spike here. Now, why is this oscillation? Because you have an inductive behavior of the ferrite bead with the 0.1 capacitor. It's now causing an oscillation. A Q is very low because you have low resistances there. And if I look inside at the frequency of this oscillation, I can see that it is about like 0.7 megahertz, and here it's 2.7 megahertz. Well, that's exactly where this unit is inducted. So you see that in this particular case, this ferrite bead is really very harmful. It is just adding a lot of noise here. However, if I look at the current passing here and passing here, in the two cases, we see that with the bead, well, we see the low frequency, the 100 kilohertz. This is the base frequency, but we have a fairly small magnitude of current of the high frequency, while without the beat we have a very large spike. So the beat is first introducing this oscillation and then attenuating the current that goes to the source. Well, I don't know if it's worthwhile, but this is the situation. So now I'm going to try something else, and that is to replace the 0.1 microfarad by 10 microfarad capacitor. Now, what is the idea behind it? First of all, the oscillation, the frequency of oscillation will be much lower because now the capacitor is larger, and with the given inductance, with a larger capacitor, the frequency of oscillation will be lower. Secondly, the Q of the system, which is Z over R, is going to be smaller because Z is L over C. Now I've increased C, so Z is now the characteristic impedance is now much lower, and for the given resistance, and the resistance is the total resistance here in this oscillation loop, okay, the 12 milli plus the 50 milli here, then the Z is much lower. So therefore, for the given resistance, it may not oscillate at all. Q might be even lower than 1. And lo and behold, this is exactly what is happening. So you see that by replacing the 0.1 microfarad capacitor with a 10 microfarad capacitor, I've sort of eliminated the oscillation. And what I'm left with is with the base frequency, the 100 kilohertz of the injection. For this, if I like to lower it, I need a much larger electrolytic capacitor, of course. It has nothing to do with the oscillation. And obviously, if I like to eliminate the injection into the source, I need a larger impedance to handle this lower frequency. Now I'm comparing what happens with the ferrite and without the ferrite. But now I've put here sort of an impedance that might represent a line between the source and our system, okay? 5 milliohm, 30 nanohenry, trace, and maybe a ground plane that represent what is really happening. Now, if I compare now the two cases and look at the current and at the voltages, here is what I see. Let's first of all start with the voltages here. You see that in the case of the ferrite, I have a lower DC voltage, and this is because we have a 290 milliohm RDC of the bead, so it's a little bit lower. See this difference? It's 1 amp times 290, it's about 0.3 volt. The ripple in the two cases on the inverter, you might say, is about the same, okay? It's about the same. But look here, this is now the current injected back to the source. IV2 is just the line without the bead, and this is with the bead. So you see that the bead now is functioning without the harmful effect of the inductance, because the frequency of oscillation is low, and at this region the quality factor is low enough so it won't oscillate. So let me summarize what we have seen here. First of all, I've tried to clarify what is a decoupling capacitor and what's the purpose, what we are trying to do. And then I give some warning about the ferrite beads, which could be helpful, but you have to be extremely careful, first of all in selecting them, and then in actually testing by simulation and actually on the hardware how they function. It's not obvious. There are many kinds of ferrite, and you can adjust the particular ferrite to a particular application, but you have to be extremely careful about that. And thirdly, I've stressed the importance of the series impedance. Without a series impedance, you cannot decouple system. you have to have some sort of a series impedance, and of course you have to worry about voltage drops, things like that, but there are some, for example, ferrite beads which are for high power, so therefore they will have a low RDC resistance and the voltage drop will be low. So this brings me to the end of this presentation. I thank you very much for your attention. I hope you found it of interest and perhaps it will be useful to you in the future. Thank you very much.